Okay, so think about the music you stream or the phone calls you make. They all sound pretty perfect, right? Crystal clear. But what if I told you that every single digital sound you hear is actually built on a foundation of tiny, unavoidable mistakes? Today, we are pulling back the curtain on the hidden world of round-off errors in digital filters. We're going to go find the ghosts in our digital machines.
So that begs the question, is that digital process really flawless? Well, the answer, and this might surprise you, is a definite no. And figuring out why reveals this fundamental tension that's really at the heart of all the technology we use every day.
All right, let's map out our journey. We're basically going to follow a signal as it makes its way into a digital filter. We'll kick things off by busting the myth of digital perfection. Then, we'll see how errors get introduced the very second a signal enters the system. After that, we'll look at what happens during all the math, the bizarre glitches that can pop up, and finally, how engineers cleverly wrangle this whole messing reality. Let's get right into it. The root of this whole problem is this epic clash between two worlds. In one corner, you've got the perfect, infinite, beautiful world of mathematics. And in the other, you have the very real, very limited world of computer hardware. It's kind of like trying to pour the entire ocean into a coffee mug. Something's got to give, right? So here's the bottom line. Think of a number like pi. It goes on forever, right? But a computer processor, well, it doesn't have forever. It doesn't have infinite space. It has to store numbers using a fixed number of bits, say 16 bits, or 24, or 32. And that means at some point it has to chop the number off, or round it. That tiny little approximation, that's it. That's the first seed of error being planted. So let's trace this error back to its source. Picture a smooth, real-world analog signal, maybe the sound of my voice. For a computer to do anything with it, it has to cross this border into the digital realm. And it does that through something called an analog-to-digital converter, or an A to D converter. This is the first hurdle. And yeah, this is where the trouble starts. The key word for this whole process is quantization. Now, what is that? The best way to think about it is like you're measuring a pencil with a ruler that only has markings for whole inches. No half inches, no centimeters. So if your pencil is, say, 7.3 inches long, you have to make a choice. Are you going to call it 7 inches or 8 inches? You're forced to round. You're forced to approximate. That's exactly what quantization is. You're squishing a smooth, continuous value into the nearest available digital box. And this visual just shows it perfectly. Over on the left, you've got that nice, smooth analog curve. Then, in the middle, the A to D converter gets to work, forcing that beautiful curve onto this rigid, blocky grid. And what's the result? This stair-step signal you see on the right. It's close, but it's not perfect. And that little gap, that difference between the original and the new digital version, that's our first bit of noise. We call it quantization noise. And here's the really crucial part. This noise, it doesn't just disappear. It's now baked into the signal. It's like a tiny bit of static that's going to follow that signal through the entire filter. And what's worse, the filter's own math can actually end up making that noise even louder. Okay, so our slightly imperfect signal is now inside the processor, and the whole job of a digital filter is to do a bunch of math on it. Just a series of multiplications and additions to shape the signal. But this is where the errors really start to add up, literally. Remember how our system can only handle a certain number of bits? Well, think about this. When you multiply two 16-bit numbers, the answer can actually be up to 32 bits long. But if your system can only store 16 bits, what do? You have to round the result, again. So every single calculation, every multiplication, introduces another tiny little puff of digital noise into our signal. And this is where we can go from tiny, almost unnoticeable errors to potentially catastrophic ones. The numbers inside a filter can sometimes get really, really big. So what happens when a value gets bigger than the maximum number that the system's bits can even represent? This is a huge problem called arithmetic overflow. Now, engineers have a couple of ways to handle this. The first, and it's a weird one, is called 2's complement overflow. In this case, the value just wraps around. Imagine hitting the biggest positive number possible, and then the very next step is the biggest negative number. It's just like a car's odometer hitting 9999999 and rolling right over to all zeros. It can cause a massive, jarring glitch in the sound. The other method is called saturation arithmetic, and it's a lot more what you'd expect. If a value gets too big, it just gets stuck at the maximum. It clips. It's exactly like a measuring cup. Once it's full, you can keep pouring, but it's not going to hold anymore. The rest just spills over.
So let's recap. We've got quantization noise from the very beginning. We've got round-off noise from every single calculation, and we have the potential for these huge overflow errors. So what does all this actually do to the filter's final output? I mean, what do we actually hear or see because of this?
Well, one of these strangest things that can happen is something called a limit cycle. These are bizarre, self-sustaining oscillations. The filter basically starts creating its own signal out of thin air. It's a real ghost in the machine. You could be feeding the filter absolute silence, a totally zero input, and the filter can start humming or buzzing all by itself, just because of these tiny internal round-off errors feeding back on themselves over and over.
And these limit cycles come in two main flavors. You've got granular ones, which are usually just a faint, low-level hum in the background, caused by all those everyday little rounding errors. But then you have overflow limit cycles, and these are the dramatic ones. These are the things that cause loud pops or clicks or even a violent screeching sound. They're caused by that odometer-style wraparound we just talked about, and they can be so bad they can even crash the entire system.
Now, besides those weird cycles, the much more common effect is simply a gradual buildup of noise. All those tiny, random rounding errors from all the math just start to pile up, and the end result is that the background noise level gets higher, which, in technical terms, degrades the signal-to-noise ratio. Basically, it means your clean signal gets a little less clear, a little more buried in a sea of this digital static. So, after all that, it might sound like our perfect digital world is actually built on a house of cards. But it's not. And this is where the real genius of engineering comes in. See, you can't get rid of these errors entirely, but you can absolutely manage them. And that is the whole game.
And how do they do it? Well, the main weapon in their arsenal is simulation software. In fact, the source material for this whole explainer says it right here. The central theme is the generous use of tools like MATLAB to figure all this stuff out before a single piece of hardware ever gets made.
So using these tools, engineers can basically build a digital twin of their filter inside a computer. They can throw everything at it, they can see where the noise is going to creep in, they can even try to cause those weird limit cycles just to see how they behave. And this lets them make smart choices, like deciding whether to use wrap or saturate for their overflow, to build a system that's going to be tough and reliable out in the real world. And really, this is the main takeaway. The idea of digital perfection, it's a myth. Great engineering isn't about chasing some impossible ideal. It's about deeply understanding and cleverly managing imperfection. Through all this analysis and simulation, we can build digital systems that work incredibly well, containing all these little errors so that to us, the end users, they're completely invisible. So, the next time you're listening to a perfectly clear song or on a call that sounds amazing, just take a second to remember that hidden world of tiny managed flaws that makes it all possible. It's a pretty cool reminder that in our digital world, perfection isn't really the absence of flaws at all, but the brilliant management of them. Thanks for tuning in.